Let's talk limit laws. If we're trying to do complex analysis or real analysis for that matter, we need to study the derivative. The derivative is a limit, and so we need laws to help us understand these limits. So right here, I've listed 4 simple arithmetic limit laws. We have a sort of a generalized statement here. We have functions whose domain is an arbitrary metric space and whose range is the complex numbers because we're interested in complex analysis. I want to point out, because the real numbers are a subset of the complex numbers, this includes the case that f and g might map from any metric space into the real numbers as well. So here we have 4 arithmetic limit laws. We have the limit of the sum of 2 functions as we approach some point is the sum of the 2 limits. The limit of the difference is the difference of the limits. The limit of the product is the product of the limits. And the limit of the quotient is the quotient of the limits. So everything works out as nicely as you could expect. There's a bit of a caveat here. Limits, of course, can exist or they can fail to exist. And so we need to think about what are the existence conditions on the right and left-hand sides of these equations. If some of these limits exist and others don't, then these equations can't possibly be true. So this theorem is actually assuming that the right-hand side of these equations exists in every case, which means we're assuming that this limit exists and we're assuming that this limit exists. We're not assuming this one does. We're saying if these two exist, then this one exists and is equal to their sum. And similarly throughout, we're assuming this and this exist, we're assuming this and this exist, and then therefore this will, and that'll equal to the combination of those limits. In the case of the quotient, we're assuming that the right-hand side exists, which is actually 3 assumptions in this case. We're assuming that this limit exists, we're assuming this limit exists, and we're assuming that the quotient exists, meaning this limit cannot be 0. Under all of those conditions, then this limit here will exist, and the limit of the quotient will be the quotient of the limits. So these are the simplest arithmetic limit laws that you could hope for, and they're all true, and we'll prove them shortly. This is a generalization of them, which once you see that there's a repeating pattern here, this is the law for plus, the law for minus, the law for times, the law for divided, then this is an abstraction of that pattern. If you have any continuous operation, which I'm writing box here from C cross C to C, then the limit of the box of the functions is the box of the limits of the functions. And that's, again, provided that the right-hand side exists. That's a convenient generalization, and we're actually going to use this in the proof. We're not going to prove all of these. We're going to prove this one, and then we're going to use it to deduce these things. 6 is a kind of an oddball limit theorem. It actually has different assumptions from these, different setup from these. This is about the composition of functions, and it's a simple statement about what happens when you have a continuous function inside the limit. So let's focus on this form here. If we have the limit as x approaches x naught of f of g of x, then this statement is reassuring us that that function can be pulled outside the limit. So we can get f of the limit of g of x. Now, that's provided 2 things. First of all, f itself has to be continuous at that point. And second, the limit of g of x has to actually exist, because otherwise this equation wouldn't make any sense. So the limit of g of x is assumed to be y naught, and f itself is assumed to be continuous at the point y naught. And then we have the limit of f of g of x is equal to f of the limit of g of x. That allows us to pull any continuous function outside the limit, which is convenient to do if we're trying to compute a limit. We're going to try to pull those functions out so that we can simplify the actual limit computation here. So here, the conditions on f and g are basically that they map from metric spaces, and the metric spaces are chosen conveniently so that they can actually be composed here, right? G goes from x to y, and then the domain of f has to be the codomain of G. And they have to be metric spaces so that it makes sense to talk about limits. So our agenda here is we're going to talk about the sum law for limits first. We're going to do this one. And as I advertised, we're going to do this first, and then we're going to apply it to this. But that's going to be confusing if we jump right into it. So the first thing I'm going to do is we're going to provide a direct proof of the sum law for limits. And you'll see how the basic structure of these proofs works. And then using that as a model, we'll prove this, and then we'll go back and revisit the others. So let's prove the sum law for limits. So here's the setup. We have some arbitrary metric space x with a point in it x naught. We have 2 functions, f and g, which map to the complex numbers. And then, of course, we also have the derived function f plus g, which maps to the complex numbers. And we're arguing about limits, so I've just copied the definition of a limit here. The limit as x goes to x naught of f of x is the certain value L, such that for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in the complex numbers, if this distance between x and x naught is less than delta, then this distance between f of x and L will be less than epsilon. So in simple language, however close you want f of x to be to L, that proximity measured by epsilon, then there is a close enough to x naught, there is a proximity delta, which measures how close you have to get to x naught, so that for any x which is actually that close, but not equal to x naught, because this is a strict greater than 0, for any x which is that close, then indeed f of x is the required proximity from L. So that's in sort of simple English what the definition of the limit says. And we're going to apply this definition. We're assuming that f and g satisfy this. We're assuming that the limit of f of x is defined and the limit of g of x is defined, and we're calculating the limit of f plus g. So, so let's start the proof of the sum law for limits. So proof of 1. So we're going to let a be the limit of f of x. All the limits are going to be x approaching x0. And we're going to let b be the limit of g of x as x approaches x0. So then what do we know? We know that for any epsilon, there exists a delta such that we can make this happen with respect to f of x and a, and with respect to g of x and b. Now I'm gonna leave a little space here, and then we're gonna dive into the demonstration that f plus g has the limit, and the limit is a plus g. So, so I'm gonna leave a little space, and then to begin the proof that the limit of f plus g is what we think it will be, we'll say let epsilon be greater than 0. Now, I'm going to choose delta, but I don't know how to choose delta yet, so I'm just going to leave that blank for now. And then I'm going to let x be an arbitrary element of the domain x. And I made a typo here. That should be in the domain. So let x be an element of this domain. So we want to think that it's around here, it's close to x naught, but not equal to x naught. And we're going to assume that 0 is less than the distance between x and x naught is less than delta. And then we're going to calculate the distance between f plus g evaluated at the point x and the intended limit, which of course is this value a plus b. So then let's calculate that distance. F of x plus g of x, that's the value of the function f plus g evaluated at the point x, minus a plus b. That's the anticipated limit. Then this guy gets rearranged in the obvious way. That's f of x minus a plus g of x minus b. And then here we have an absolute value of a sum, so we apply the triangle inequality, and we get f of x minus a absolute plus g of x minus b absolute. And this is great news because this is a function, this is the value of the function compared to its limiting value. This is the value of a different function compared to its limiting value. And so, so we expect both of these to be small. And we can have control over each of these because we know that the limit of f of x as x approaches a, x naught is a, and we know this other limit as well. So how do we get control over both of these? Well, we make sure that x is close enough to x naught, and we can have control of this. What kind of control do we need? We need each of these to be less than epsilon over 2. And how do we get that sort of control of these? Well, if x is less than some delta for the limit of f of x, then f of x minus a will be less than epsilon over 2. And so we need to choose this delta. So that's what this space here is for. We're going to make those choices of delta. So we're going to choose some delta 1. So for epsilon over 2, in the definition of the limit as x goes to x naught of f of x is a. And what this means is, so in the definition of we're going to choose delta 1 for x naught. What we're doing is we're saying this is assumed. It's assumed that for all epsilon there exists a delta. So I'm going to apply this to the value epsilon over 2, and then there must be a delta, and I'm going to call it delta 1. So that's what that means. And then with delta 1, I know that for any x, if this distance is less than delta 1 and greater than 0, then f of x minus the value a will indeed be less than epsilon over 2, which is the guarantee that we need right here. So we're going to choose delta 1 to be that, and then we're going to do the same thing for delta 2. So choose delta 2 for epsilon over 2 in the definition of the statement, the limit as x goes to x naught of g of x is equal to b. And that's the delta 2, which guarantees that so long as x is that close, then this thing will be bounded by epsilon over 2. How do we, so now all we have to do is fill in this blank here, so that when we assume that the distance between x and x naught is less than delta, we will have effectively assumed that the distance between x and x naught is also less than delta 1 and also less than delta 2. And so we need the assumption that it's less than delta to imply both of these assumptions. And so we'll choose delta to be the min of delta 1 and delta 2. When delta is so chosen, then this assumption, which tells us this distance is less than delta, forces the other assumptions that it's less than delta 1 and less than delta 2, which forces both of these statements less than epsilon over 2 to be true. And that gives us the epsilon that we need, which finishes the proof. For every epsilon, there exists a delta, namely this one, such that for every x, if this is true, then this computed thing is less than epsilon, which directly shows that the limit of f of x plus g of x is equal to the a plus b that we anticipated, which is here. So that establishes the sum law for limits. Now, the other laws can be done the same way, but in the next video, we'll show that we're going to do the generalized version first, and then we're going to start deducing these other laws from the generalized version. We could have done the same thing for addition too, but it would have been too confusing. So stay tuned.